We have another structure here with two members, and in this case we have them connected at point C here. So this one would actually be over here, as you can see in the book. So we have an equal and opposite internal reaction at point C. We have this bar is pivoted pinned to ground at point A, and this one is pinned to ground at point B. And then we have an external load acting at either point E or at point F. So again, we're asked to look at the two different cases, and I'll just look at both of them at the same time. So in this case, so we have it's going to be either 100 load, 100. It's going to be a minus 100 pounds in the downward direction, either at point E or at point F is what we're going to have. And so we can go through the process again, right? Position vectors to our point. I used A as the origin, so we have positions to B, to C, to D, to E, and then to F. And what I did is in the first set of equations, force and moment balance, I looked at the whole structure, the entire structure. So force C cancels out, so we just have A, B, E, and F acting. So we need those to sum to 0, and then we need the moments that they create to sum to 0. And in the second case, for the second set of equations, I used just this structure here. And so that's on that we have forces B, C, and E. And obviously C doesn't cancel out in this set of equations. So then we have another set of force and moment balances to keep this in equilibrium. This stays in equilibrium if both are in equilibrium. If the combination is in equilibrium and one of them is also in equilibrium, then they both are. I could have used A, C, and F here if I wanted to. I would get the same answer. So we have 6 unknowns in our equations, the two components of each of these two reaction forces, and the two components of our internal load here. And we have 6 equations. So in them at the thing now the problem is just algebra. And if we go through the algebra, I solved it in general for general FE and FF. And so we can set one of them to 0 and set one of them to 100 pounds and look at the different results. And if we set, if the load is applied at point E, so down here, kind of, we see that we get these reaction forces at A and B. And if we apply the load at point F, which is up here on this upper bar, we see that the horizontal component of our reaction forces is 0, and because we're not creating a moment basically that needs to be offset. Here we're creating a moment that is basically causing the horizontal components in these reaction forces. But when we play it up here, then we aren't, and then basically this being in equilibrium, FC, I believe in this case, is also just purely vertical. So in this case, when we apply the load here, we only have vertical loads, and so we can see that depending on what we wanted to do, we either have larger horizontal loads at the pin joints.